2017.
My name is Chris Kralinski. I'm a hacker from Canada, and I'm here today to talk about how to break the code read protection on the NXP LPC family of ARM microcontrollers. So the LPC family of microcontrollers, they're a low-cost 32-bit ARM microcontroller. There's a variety of parts in the family. They have an internal flash ranging anywhere from 8 to 512 kilobytes, and from 1 to 282 kilobytes of RAM. Different parts from the family have a different set of various peripherals, including the UART, USB, CAN, and Ethernet controllers. There's a variety of parts in the family. They all share a lot in common. It's mostly the peripherals and the memory size that differs between them. Inside of the parts, they have a bootloader for in-system programming. So this bootloader allows you to load your program into the flash area. It's quite a simple bootloader using a serial protocol. There's a list of the available commands here, including to write to flash, also to read from flash using the ISP interface. There's existing software that you can use to use the ISP interface. There's a software from NXP that runs in Windows. There's a nice open source program called LPC 21 ISP, and there's some others too. You could write your own quite easily. They have all the documentation for this protocol in the data sheets. Inside the bootloader, they have support for CRP, or code read protection. They have 3 levels of the code read protection that they've defined. The CRP level 1 will disable the read command in the bootloader, but it does still allow flash writes to some areas of the chip. The CRP level 2 will disable the read command and also disable all flash writes. And then the CRP level 3 will disable all of the commands, and it will also disable access to the bootloader entirely, so you have no access to the in-system programming. Additionally, they have a 4th level that they call no ISP, which doesn't disable any of the debugging features in the chip, but it does disable the serial bootloader. So that's an additional option. For the CRP levels 1, 2, and 3, in any of these, the debugging will be disabled. So here we have a flowchart showing the boot process inside the ROM bootloader inside of these chips. So we can see from reset, it does some initialization. It will do a check then to see if the code read protection at any level 1, 2, or 3 is set. If the code read protection is set, then it will disable the debugging. Otherwise, it will enable the debug interface on JTAG. It does some other checks, like checking if the watchdog flag was set, and if so, then it will go back into the program because it had a reset due to watchdog. Otherwise, it will continue and it will check if the code read protection level 3 or the no ISP are set, because these ones will disable access to the bootloader. If they're not set, then it will check to see if you're holding one of the GPIO pins low that triggers the access to the bootloader. If it does not go into the bootloader, it will go into the application, but before it goes into the application, it will check if it considers the flash code valid. And it does this by calculating a checksum of the first area of the vectors inside flash. If this checksum is valid, then it will jump to the reset vector inside flash. Otherwise, it will fall through again into the bootloader interface. Some of the chips have a USB bootloader in addition to the serial bootloader. Some of them don't. Some of them don't support the USB. If they do support the USB bootloader, then it will determine if you have the USB connected by checking if there's a high voltage on the V-bus pin of the chip. So if you want to disable the USB interface and access the serial bootloader instead, you have to hold the V-bus pin low. And if all these conditions are met, then eventually it will execute the serial bootloader out of ROM. So we can see that they use a 32-bit word in Flash to define if the code read protection is set. So they have 4 values which will enable some level of code protection inside of this chip. If any of those 4 possibilities of the 32-bit word are set in this location in flash, then there will be some locking set. If any other value exists in this location in flash, then the chip is going to start up in the bootloader and be totally unlocked. So out of the possible 32-bit words, there's 4 of them that will lock the chip, or 4,294,967,292 that will result in the chip being unlocked. So we can see already that this might be a rather fragile lock on the chip, that there's some good chance that we might be able to trigger it to read incorrectly. This is the memory map of one of the parts. This is for the LPC 1343 chip. The other members of the family are quite similar as far as the memory layout. Some blocks might be moved around. We can see that the flash starts at address 0, and they also list where the boot ROM is, starting at address 1FFF0000, and they have a 16K byte bootloader inside of this chip. Most of them have a very similar boot ROM. Some of the parts, like the LPC 2148, actually have a bootloader inside of a flash area at a different memory location, but in general, they're quite similar to this setup. So here are just some quick links for some useful tools for using the LPC chips. The first one at the top is the LPC 21 ISP. This is a nice, simple, open source software to program the LPC family microcontrollers from the command line. And then also I've shown some links for various example codes to use the GCC ARM compiler to be able to write programs that will run on these chips. Another option is to use the official toolchain supported by NXP, but generally that's going to be Windows compilers, and some of them you actually have to pay for to get the full feature set. So it's kind of nice to be able to work with GCC and have a more standard tool chain where everything is free and open. So to start out, we're going to want to see what they're actually doing inside of the boot ROM. So I write a very simple program that I can load inside of a blank LPC chip, and I put a function like this inside that simply sets up a pointer, and start with the pointer pointing to the beginning of boot ROM, and then read 1 byte at a time and output them out the serial port. Because the example code that's available is quite nice and complete, and supports a lot of the standard C library functions. We have even printf, so it makes it nice and simple and clean to be able to read the memory out of this chip. So using a function like this, we can load it into the chip and have it send us the contents of the boot ROM so that we can see exactly what it's doing inside the bootloader. So this is the beginning of the bootloader, the first code that executes after the chip is reset. This is a disassembly of a part of the code. So we can see that the very first thing that it does is it's going to check if the CRP level 1, 2, or 3 is set. And if they are set, then it will disable the debugging. Otherwise, it will enable the debugging. So we can see what they do here is if the CRP 1, 2, or 3 are set, then they're writing the value 87654321 to the register at 400483F0, which isn't documented, but clearly this register is what enables or disables the debugging. So again, if they write the one specific value to this register, it will disable the debugging interface. If anything else is written to this register, then it will actually enable the debugging interface because the chip is considered unlocked. So in the first part here, they're setting up whether the debugging is enabled or not. And now we can continue on to the next piece. I've cut out just segments of the boot ROM to cut out the irrelevant parts so that we're not looking at too much disassembly here. So what they will do next is they will look at the value in flash that defines if the code read protection is set. And they're reading this value out of flash, and they're storing it in a variable inside of RAM. In this disassembly, I've labeled this variable CRP value in RAM. And then later on in the code, we can see that they start to do some comparisons to see what CRP level is set. In the middle segment of the disassembly here, they're checking if the CRP level 3 is set or if the no ISP value is set. And if either of those are set, then it's going to jump into the application. Otherwise, it's going to check to see if we're holding a GPIO pin low to trigger the bootloader. And they're doing this comparison not directly against the value in flash, but they compare against the variable that they've loaded into RAM already. In this screen here, this is a function that I call select bootloader. The boot code is going to end up in this routine if we don't have the no ISP or the CRP3 enabled, and if the bootloader has been triggered. So at this point, it's going to check to see if it should go into the USB bootloader or the serial bootloader. And again, we can see that they do the same thing where they're reading the value from flash for the CRP, and they're storing it in, again, the same variable in RAM. So at this point, they have the CRP value, if it's set, stored in their variable in RAM, and they're ready to enter the serial ISP software. So in the serial ISP routine, this is the very beginning of it, we can see that they set up some registers, and they're setting registers R6 and R7 here to be initialized with the values that would enable CRP level 2 or CRP level 3. And then they're continuing directly into their command loop where you can send the ISP commands via the serial interface. This is deeper into the ISP routine. This is after you've sent it a command, and it is going to check the command to see if it's on the list of commands that would be disabled if code read protection is set. So we can see that right from the very top, I've started where if it's a command such as a read or a write to flash, then it will set register R2 to 1, which indicates later in the program that this is a command that would be disabled by CRP. And then they're going to continue and they're going to check to see which CRP value is actually set. Now, if we look here, we can see that they're actually doing the CRP check against this variable that they have in RAM at this point. So inside of the serial bootloader, when they want to know, is this command allowed, they're always comparing the CRP value, the lock value, against this value that they've already loaded into their variable in RAM. So at this point, they're not even looking into the flash anymore to see if it's locked. They've loaded this value after reset, and now they're able to just check in RAM every time. So to continue from here, I am ready to start testing on the chips. So I took a variety of chips from the family and I mounted them on different breadboards. So this is one of the smaller members of the LPC family. This is an LPC 812 on a breakout board. This is another smaller member of the family. This is the LPC 1114. This is the LPC 1751, and you can see I've only populated some pins on the breakout board. This is because really I only need to power the chip to enter the bootloader mode and to have the serial access. I'm not interested in so many of the other peripherals, so I try to keep it simple. This is an LPC 2101, another member of the family. And this is an LPC 2148 on a nicer breakout board that I found with a ZIF socket. That's a lot more convenient to work with if you're going to be changing between a lot of different chips. And then another option is also to use a pre-made development board. This is an Olimex board for the LPC 1343 chip. This one has been modified a little bit. I've removed two of the capacitors C1 and C4. These are the filter capacitors on the VDD pins because I'm planning to glitch this chip, and that's going to involve quickly dropping out the power supply, so I don't want those filter capacitors. They're going to be trouble for me. Also, I've cut 2 traces on the board, which are for the VDD and VDD I/O signals. This development board is set up nicely that they give you a spot specifically to cut if you want to disable the power supply from the board. So I've installed jumpers on those locations so I can connect with my own power connection. And then also I've added this green wire, and this green wire is just connected between the ground pin on the debug port and the VBus signal going into the chip, because normally this development board is designed so that you'll be using the USB bootloader. So in order to disable the USB bootloader, I've added this green wire, which is simply holding VBus pin low. So we'll enter the serial bootloader instead. So this is my basic setup that I use for glitching chips. At the top, I have an oscilloscope that I use so that I can actually see a little bit of what's going on. Below that, I have a power supply, a dual output adjustable power supply, so I can set 2 voltage levels independently. In front of that, I have a little mess of wires and development boards with an Atmel XMega board that I use for controlling my glitch and for doing the serial connection to the chip. I have one of the LPC boards on a breakout board. I have another small breadboard with the actual glitcher circuit that I'll get into more in depth in a few more slides. And then I have the oscilloscope probes connecting. In the background, I have the computer that it's connected to. On my computer, I'm just running Minicom. I have just a direct serial interface to the XMega board that I'm going to be using, and I run a little terminal program within the XMega, and this is my interface for the glitcher. So to have a bit of an idea of what's going on inside of the chip during boot up, I do some simple power analysis on this chip. To do a power analysis, I connect a 10 ohm resistor in series with the ground signal going to the chip. These measurements are from an LPC 812 chip. And again, as I noted, it's simply a 10 ohm resistor in series with ground, and I measure the voltage across this resistor. So as the power consumption of the chip is changing, you see a difference in the voltage measured across this resistor. And then on the oscilloscope, we can get these traces which look quite noisy, but still we can see that there's some pattern to it. The image at the top left is showing immediately after resetting the chip and entering into the application. And then the image at the bottom right is showing when we reset the chip and it enters into the bootloader. So we can see that the left half of the image is quite similar between the two of them. And then around the middle of the oscilloscope image, we start to see that there's some differences in there. So we can't see exactly which instructions are being executed, but we can clearly see that there is some difference in the code path that's being taken. So this is a measurement of the same thing. Again, it's the reset and starting the application, comparing to reset and starting the bootloader. I've marked with cursors on the scope here, so we can see with the yellow lines the exact point at which the code flow starts to differ. So we can gather from this that the part between the two yellow cursors at the left of the image, this is the boot ROM code, the initialization and the initial checking of the code read protection. And then everything to the right of the cursor differs depending on whether we've triggered the bootloader mode or whether it's going directly into the application. So this is a video showing the live image from the oscilloscope. Right now it's starting into the bootloader mode, or it was in the boot application mode. This is going into the bootloader mode. Now it's switching back to the application mode. So even though it's noisy and it jumps around, you can see some different patterns as it switches between the bootloader and application mode. So even with these dirty signals, we're not going to get all of the detail that we might really want, but it's definitely enough to be able to see if the code flow is taking the path that we expect or if it's going in some different direction. This is showing on another chip. This is looking at the LPC 1343. So the very top trace, I'm measuring the power consumption using a resistor in series with the VDD pins. And then near the bottom, I'm measuring the power supply with the resistor in series with the ground pins. So you can do the power analysis on the VDD or on the ground. Generally, you'll get a nicer, cleaner signal measuring off the ground. I mean, we can see some differences in this image, on either trace, whether we're looking at the VDD or the ground. But clearly, the bottom tracer with the ground is much easier to actually see some differences in what's going on as we trigger between the bootloader and the application mode. So to get into glitching, my glitcher is based entirely around this chip. This is a MAX 4619 chip. This is almost the entire glitching circuit right here in this one chip. The MAX 4619 is a chip that contains 3 single-pole double-throw switches with a fast switching time and a low series resistance when they're switched on. So what this means is that we're able to switch between 2 inputs, and that will adjust the output level. And we have switching times that are as low as 10 to 15 nanoseconds. So this means that we can very quickly switch between 2 voltage sources, and this is how we'll actually produce the glitch output. So this is a diagram, again, from the MAX 4619 datasheet, just showing the actual circuit inside the MAX 4619. And you can see it's quite simple. It really is just 3 switches inside. So we have 3 inputs, Y0, Y1, X0, X1, Z0, Z1, and then the 3 outputs are the X, Y, and Z outputs. And the controls for these switches, which selects the 0 input or the 1 input, are A, B, and C. There's also an enable pin, which if you hold it low, then the MAX 4619 will output voltage to the chip. If we release that high, then it won't have any output to the chip at all. So we can actually use this to be able to completely cut off the power supply to the chip. So this is the schematic of the glitcher circuit that I use. All that I've done here is I tie the 3 switches in the chip together in parallel. So I do this, it helps to lower the effective resistance that we see through the chip, so it has a little bit less effect on the voltage level itself. They'll still switch together very fast. I only actually need 1 switch because I'm only switching one thing, only the VDD towards the chip. So I've tied the Y1, Z1, X1 signals together, and I've tied the Y0, Z0, X0 signals together. The same with the control signals A, B, C. So the outputs from X, Y, and Z1, or sorry, the inputs to X, Y, and Z1 are coming from my power supply, and those will be the glitch voltage level that I set, while the input 0 is the normal power supply level that I set. And then the outputs X, Y, and Z are the output actually going to the target chip. So to control this, I just need 2 signals. I'm running these to my Atmel XMega development board that I use. So the enable pin, I run to the XMega port A3, which allows me to enable or disable the output to the chip entirely. And then the control pins A, B, C, I'm running to another XMega port A0. And this is how I'm going to switch between the normal and the glitch voltage levels. So this is the actual circuit with the MAX 4619. This is basically the whole glitcher board, minus the XMega that I use as a microcontroller. I like the solderless breadboards. They're very convenient to work on. They allow you to change your ideas very quickly and test different things out. Any problems with high frequency noise or anything like that, really for most of the projects that I do, I don't notice too much of a problem with it. I'm able to ignore it and kind of do things the cheap and easy way. So I enjoy that I'm able to just pop a chip into the breadboard, connect these wires, and in a few minutes I've built a glitcher like this. So this is a picture of an LPC 812 chip connected to the glitcher. As you can see, I'm very careful always with my wiring, keep everything nice and neat. But really, as I said, the noise and things that you see, in most cases, it's only a minor annoyance, and everything's actually still going to work. So I like this quick and dirty method of working. This is another angle of the same glitcher setup. Again, showing off the nice clean wiring that I tend to do. So here I have everything labeled. The blue development board is an XMega A1 explain board. This has an Atmel XMega chip, which is an AVR that runs at 32 megahertz. Then below that, on the black breadboard, I have the MAX4619 glitcher circuit. You can see that I have a 10 ohm resistor that I put in series with the ground going to the LPC 812. That's how I'm doing the power analysis. So I simply put that in series with ground, and I connect the oscilloscope probe to the side of the resistor that the LPC chip is connected to, and that's going to be my power analysis signal. And then at the top right, you can see that there's the LPC 812 that I've mounted on a breadboard for testing. For the power supply to control the VDD levels to this chip, I use a benchtop power supply. So it has two outputs. The first output, I can set the normal VDD level that the chip will run at, and then I'm going to use the second output, and that's how I'm going to adjust the level of the voltage drop while I actually perform a glitch on the chip. There's lots of different options actually for supplying power to the chip, or you could build a circuit and be able to have it digitally controllable. Personally, I like the hands-on method of having a benchtop power supply like this. Again, it lets me quickly connect different things and test different ideas if I want. And I find it a very nice way to work, to actually be able to adjust the knobs and see the difference in the output. And it's nice and quick and easy just to connect everything together. So this shows the development board together with the breadboard with the glitcher circuit. So this is essentially the whole glitcher circuit minus the target board with the LPC chip and without the power supply. So at the very top, we can see where the inputs from the adjustable power supply will come from. So the white wire is going to be ground from the power supply. The red wire is the normal voltage level, and the green wire is the second voltage level that we'll use for the glitch. Then we have the VDD and ground output towards the target chip. And then other than this, we'll also have the serial port, the UART, connected between the LPC chip and the explained development board. But as far as the glitching circuit goes, this is the entire system right here. Well, that's very dark. So I don't know how well you can see this because of the colors that I have, but this is the C and assembler code that I run inside of the XMega chip to actually control the glitching. So the basic concept is that I use the out instruction on the AVR chip. So the out instruction is a single cycle opcode. So this means that if we're going to execute a series of out instructions, we can actually change the output signal on the port at every clock cycle at 32 megahertz. So that means that we could actually trigger a glitch that would have a length as low as 31.25 nanoseconds. It'll be a little bit different than that actually because of the switch on and off time within the MAX4619. But generally speaking, it can do quite short glitches. So what I'm doing here is I have a series of out instructions that will set the level on this output pin. And before I call my glitch function, I set up some variables to define what kind of a glitch waveform that I want. So I can have it anywhere from 1 cycle at 32 megahertz up to 8 clock cycles at 32 megahertz. And it can be changed very easily within software, and I don't have to have a separate routine for each different length of glitch. So this lets me kind of change things on the fly and still have the flexibility to have these very short glitches. So to start trying to glitch the chip, the easiest way is if I'm able to execute a glitch against code that I know exactly what the code is doing. And since these are common microcontrollers, I could buy a blank chip and I can load my own code inside. So using the GCC ARM tool chain, I write some simple C code. So what I have here is a while loop that will continue executing forever. And I have two variables that I'll use inside of this loop, A and B. And so I'll initialize B to a value that I have set as number of glitch loops, which in the case of this test, I actually have set to 16. I will toggle some GPIO pins. This allows me to have nice synchronization between the LPC chip and the AVR chip that will do glitching so that I have my timing nice and precise. And then I have in the middle a for loop. So this for loop is going to increment the A variable from 0 until it reaches the total number of glitch loops we want to do. And during this loop, it's going to decrement the B register. So what this does is normally at the end of the loop, we should know that the A variable is going to end up being 16 because that's how I have the num glitch loops defined. And the B variable should always be 0. At the end of this while loop, then I am checking to see are the A and the B values actually what I expect. If the code is operating normally, then the first condition will be true, A equals number of glitch loops and B equals 0. In this case, I'm printing out the serial port, just a dot. This indicates that there was no glitch, that the code operated normally. But if this check of the A and the B variables fails, that they have a different value, then I'm going to print out the serial port what those values were, and that indicates that some kind of a glitch actually occurred, that the code did not execute normally like it would. So I wrote this test code in C, so we could actually look at the assembler code that would be generated by GCC to see exactly what instructions are going to be executed that we're going to try to glitch. Another option would have been to write the code directly in assembler, but it's such a simple test program, and the idea is only to see if it has an effect. So I prefer it to work in C. It's a nice, easy, convenient way to work. It's a little bit nicer than having to write an assembler for everything. But we can see that what the compiler did here is really quite simple, except for all the extra noise from the listing. But basically, it starts with A equals 0, it decrements B, it increments A, and it checks to see if we've hit the end of the number of glitch loops yet. So this video is showing what I see through Minicom when I'm running the test code. So all these dots mean that no glitches happened. So I'm waiting for this for loop to start, and then I'll do a quick glitch. And as this is running, I'm adjusting the voltage level on the power supply. So you can see when I start to lower the voltage on the power supply, we start to see some strange responses come out of the chip. So all of these lines showing what A and B are indicating that a glitch occurred. The X's that come up, that indicates that the chip reset, and we can see a bunch of X's come up there at once as I've dropped the voltage level even lower. So because I start to see a lot of resets with the voltage level so low, at that point I increase the voltage level a little bit, and what I'm doing here is trying to find kind of the sweet spot where the chip runs and it still has the most strange effects coming when I glitch inside this for loop. So we can see that normally the value in A should be hex 10 and the value in B should be 0, but we got all kinds of different values depending on exactly which instruction that we glitched within the loop. We have lots of results that are like A is 5003.009. This will be because A is actually pointing to the location within RAM where that variable was stored. So because it wasn't just a loop where it was incrementing registers, it would actually have variables in RAM. So we ended up with a pointer instead of the actual value there because of where the glitch broke the loop. But we have a variety of different effects. But the main point here is just that we're having some effect on the chip. The code isn't operating normally. All that I'm doing at this point is dropping the VDD supply to the chip very briefly during that loop. So by doing this kind of a test, this lets me have a nice area to target where I can kind of tune things in and find what length of a glitch and what voltage levels will actually most likely have a good effect on the chip. So this is showing the oscilloscope image along with the Minicom screenshot showing of actually glitching during this target loop. So the top channel is our power analysis channel. The middle channel there is showing a GPIO pin. it's pulling the GPIO low while it's within our for loop that we're targeting. And the bottom line there was just reset, so it's always high during this. So we can see it's attempting to glitch, and it's attempting to glitch, and then finally it stops. And we can see that when the glitch actually had an effect, our loop got much shorter. We can see because the GPIO was held lower for less time. And on the bottom window there, we can see that we ended up with the value in A being 50030008. So again, it was set to the pointer value, not the actual value of the variable. And we can see that the B variable ended up with hex E. So B would have started out with hex 10, and it got decremented twice to F and then to E. And then at that point, we broke out of the loop. So the loop is shorter, and the B variable matches the length of the loop because it didn't count down all the way. So this is showing several screenshots of glitching and seeing different effects out of the chip. So at the top left, we have a screenshot of when we did the glitch, but it didn't actually have any effect. So the ending result in variable A was hex 10 and B was 0. Below that, we can see that the glitch had an effect. A ended up with the normal value, but B ended up with the value FF, 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 F1. So what has actually happened here is we can see that the loop was extended a little bit, and so the B variable actually got decremented more times than normal, so it ended up with the wrong value. At the top right, we can see again that the loop broke early. We have A being set to a pointer value, and then we have B set to hex E instead of being decremented all the way down to 0. And at the bottom right, we have another result that comes up, and again, it's similar to the one at the bottom left, but in this case, B was decremented down to FF, 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 F2 instead. So now if we adjust the glitch to hit at a different part of the loop, I've changed the timing, so I'm waiting a few more clock cycles before I glitch. Here it has an effect again, so we can see that the loop was shortened because of the glitch. We broke out of this for loop, and we can see again that the variable A is set to this pointer value it tends to get left at, and the variable B is now set to hex A. So the variable D got decremented a few more times because we waited further through the for loop to glitch. And here we have screenshots showing the different results that we have when we glitch at this timing location versus the first one. So we've waited through a couple more rounds of the for loop. Now something else that we can notice in these images, if you look especially at the top left image, you can see when the for loop executes, and we can see a little pattern there, and that pattern we see repeating exactly 16 times. So from the power analysis, we don't necessarily know what instructions execute, but it really is very clear that there's a for loop that's executing exactly 16 times. And if we compare to the bottom left image, then you see that it hasn't executed 16 times. You see it executes about 5 times, and then we have the glitch, the big spike on the power consumption, and then it completes one more loop and then it exits. So using this power analysis is very nice to have a much better idea of what's going on inside of the chip. It doesn't tell you everything, but you can really get a lot of clues out of it. So now this is showing a video of from reset. We can see the channel 4 there. The bottom one of the oscilloscope is the reset signal. So from the rising edge of reset is where we're starting to trigger. And then the top trace, again, is the power analysis. And as it begins here, it's entering into the application mode. And we're not able to enter the bootloader mode because we have the no ISP set. But by glitching near the location where previously we saw the difference between entering bootloader or entering application, we can actually glitch at this spot, and we're able to see very clearly on the power analysis that instead of going into the application like it is now, when the glitch finally hits and lands, the following trace on the power analysis is showing that we're going into the bootloader instead. And we can verify this by sending a command to the chip, and it does actually respond to the bootloader. So after we've done this, in my very simple Xmega code, what I've done is instead of implementing the entire ISP code myself, I simply do a serial port pass-through. So I run this process, I glitch, I'm able to enter the bootloader even though it's been disabled. And then after this step, I can drop back to the command line and I can use one of the commonly available tools. This is now able to read the flash out of an LPC 1343 chip. So it reads it through the normal ISP interface because as far as it's concerned, this is an unlocked chip. We can see the flash contents and it really is just that simple. We've been able to identify the locations in the boot ROM startup where it's checking the code read protection values, where it's checking if it's allowed to access the bootloader. We perform a glitch at that location. It's able to corrupt the code flow, but the chip still operates other than a few corrupted instructions. So we've entered the bootloader. Once we've entered the bootloader, then we can drop back to any of the LPC programming tools, and it's able to just read the chip normally as if it was an entirely unlocked chip. So I've uploaded my test code for the glitcher to GitHub. It's not exactly production-ready code, but it's what I used. It does mostly work. It's not well documented, but I guess that's kind of normal. So this is code for the Explain development board, the AVR chip, and this has my serial interface code and also all the timing code for the glitches to control the max 4619 and perform our glitching. Yeah, so if you're interested, you can take a look there. Hopefully as time goes on, I might actually clean it up a little bit and document it a bit better so it'll be a little bit more usable. It's very much a prototype at this point still, but as you can see, it does work for actually glitching the chip. Something interesting that I saw while I was working on this is that there's an application note from NXP, application note 10866. This is for a secondary USB bootloader. They do have some chips that have the USB peripheral, but they didn't include the USB bootloader in their boot ROM. So they've provided this application note explaining how you can make your own USB bootloader. And it also supports the familiar code read protection levels. What's interesting about this one, though, is that they only allow readout through this version of the bootloader if the code read protection word is actually set to one specific value that they've defined as no CRP. So we can see here that they've actually made their application note, their suggestion for the user bootloader is implemented in a more secure way than their actual ROM bootloader. There's about 4.2 billion fewer possibilities to corrupt the CRP value and actually allow the readout in this case. So clearly somebody is aware that there's some issues with the code read protection, but there's not so much that they can do inside the ROM bootloader. Now also, another thing that I looked at on this chip was looking closely at the power analysis during startup. So I have two oscilloscope screenshots here. The first one is showing the startup with the no CRP set, so there's no read protection enabled. And then the second one is showing if I have the code read protection level 1 enabled. So if I kind of flip back and forth between them, you can see that they look almost identical, except for the CRP1, just past the halfway point, there's a little pulse there that's a little bit longer. So we can see there's a slight difference in the code flow between no CRP or CRP level 1 being set. And then if we go back and we look at our disassembly of the boot ROM, we can actually see that directly in the startup, this is where they're checking if they have the CRP level 1 set to know if they can enable the debugging interface or not. So we can see from these oscilloscope images exactly where this piece of code is being executed. And I didn't actually test this, but I expect that this might actually be an even easier target than the serial bootloader to try and unlock the chip. because if you can corrupt this value that's being written to the undocumented register 400483F0, then your debugging interface should be enabled. So rather than having to deal with the serial bootloader at all, you could just plug in the JTAG debugger and read out the flash directly from this. Again, it's clear from the code that if any other value besides 87654321 ends up written to this register, you're going to have a wide open debugging port. So being able to see this code flow difference in the power analysis is quite nice because it gives us an indication exactly when we need to glitch within a few clock cycles. So I took a look also just at the chips directly. I did a quick decap of the chips. This is an LPC 2148 chip. It's one of the older series of LPC chips. This one contains the flash bootloader, not the ROM bootloader. But generally, they're all still quite similar. They're all the 32-bit ARM chips. In the corner of the chip, we have the part number and logo for the chip. Again, this is the LPC 2148. Just for comparison now, this is one of the newer series, the LPC 1343. We have, again, a nice logo and a part number in the corner, very easy to identify the chip. In another corner, we have a nice little piece of artwork here. So looking more towards the middle of the chip where we have the actual circuitry, this is from the LPC 2148. And we can see that the circuitry is quite dense. So for an invasive attack with probing, I'm sure it can be possible, but it would need fairly advanced equipment. It's going to be tough just to put a needle directly down on top of a chip like this. Also, we can see a lot of these sort of rectangular pieces of metal there, because any of the areas on the top layer that don't have metal, they filled in with filler to keep the chip well planarized. So areas on the chip that are the top layer of the chip that are empty are covered with metal like this. So we have actually not much access to the bottom of the chip without further deprocessing. And when a glitch is possible, there's not really much reason to actually do an invasive attack. But because it's so covered in metal, this does make it more difficult if you want to do a laser attack or anything like this. I mean, maybe it can still be possible, but it's a lot harder to do that kind of thing when you don't actually have access to the transistors below. So yeah, this is quite dense. This is the 2148, and the newer chips are even smaller. So from an invasive perspective, it's a little bit difficult to work on this chip unless you have high-end equipment. But the glitching works great. So the non-invasive attack is definitely the way to go. These chips are quite easy to get to glitch, and because you can read out the boot ROM so easily and it's set up in such a simple way, it's a nice target, and it's quite easy to unprotect these chips. Yeah, so that's about all that I have. I hope that I've been able to show how easy it is to build a simple glitcher to set it up. You can get a lot more advanced than this. Personally, I like to do it the simple, easy, cheap way, and it works good enough. You could get more precise with your glitch timing and with different glitch waveforms and all of this kind of thing. But I mean, in this case, all you need is one max 4619 and a power supply, and you can find that you can have an effect on the chip very quickly. And then it's just a matter of finding your target location, which again with the power analysis makes it very easy, and the code is quite simple. Yeah, so the bottom line is don't trust the code read protection too much on these chips, but it's not really too specific to the NXP LPC family. Generally, a lot of the basic microcontrollers are set up in similar ways. The locks tend to be quite fragile. So I'm not really intending to pick too much on this family of chips. This is just a nice example to work with. Most of the simple microcontrollers that have a boot ROM with a bootloader inside will have similar defects to this, that if you're able to find a way to glitch the chip, then probably you can bypass it in the same way.
Hi, I would like to ask, do you provide the clock from the glitcher circuits to the MCU as well, or is it running from an internal RC oscillator?
Yes, that's something that I glossed over for sure. These chips are generally running from the internal RC oscillator. Some of the family do need an external clock. The LPC 2148, for example, runs off an external clock. In general, the whole family does support the external clock, but during the boot ROM, it's running off of the internal clock. So for my testing, I didn't even supply a clock signal to it because it had no effect at the time of the program that I was looking at. The LPC 2148, when I worked on that one, something that I did find that was worth noting was that the development board that I was using had a 12 megahertz oscillator on it, which I was able to still glitch the chip. But when I increased the oscillator speed to 16 megahertz, the chip becomes much more easy to glitch. So if you have the ability to run from the external oscillator, then if you increase it to kind of the highest level that you can, the chips tend to get easier to glitch. But I mean, unfortunately for me, in this case, most of these chips were running from the internal RC oscillator.
I have one additional question. Have you tried using the chip whisperer?
I haven't used the chip whisperer. I've heard that it's a good tool, but I haven't actually had a chance to get any hands-on experience with it.
Okay, thank you.
Thanks.
Hello. Very nice presentation. Thank you, especially because it's quite low cost to do this type of attack. I have two kind of related questions. The first one is, how long was the glitch campaign when you were searching for the characteristics of the glitch? And the second one, once you find these characteristics of the glitch, what's the success percentage of repeating the attack?
So to find the glitch initially, on this one I was fairly lucky. I mean, this isn't the first chip that I've tried to glitch, so I sort of have the strategy that I follow. And by loading my test code inside with this for loop that I can target, it gives you a nice targeted area where you have a defined effect, if you're able to have an effect. So I think within the first day of playing with this chip, I was able to see some effects from the glitching. And then it took a little bit longer to actually find the precise points to glitch to access the bootloader. But it was fairly quick that I was able to do that. And then the repeatability, so the glitch doesn't necessarily work every time. But if you only need to do one glitch in the program to get to the point where you want, and you can try many times, then it's not so bad. So I mean, in this case, I'm having a glitch success rate of maybe 1%, but I can make more than 100 attempts in a second. So I'm still having success within a second or two.
Okay, thank you.
This talk focused on a glitch to break out of some kind of loop or bypass a conditional, and your previous talk at CCC and REcon last year had you glitching to change like a branch target, so you were jumping into a payload in memory. Do you see that certain architectures or certain processor families are more susceptible to certain types of glitches, or that you can characterize like what's actually happening in there based on some criteria?
On most of the chips that I've looked at, I haven't done so much characterization. Typically, I'm just looking for something that's going to corrupt an instruction, and the exact details I'm not so worried about as long as it doesn't corrupt too much. Depending on the architecture, it does make a difference. If you're using a chip with a Harvard architecture, where your data memory and your code memory aren't shared, then that can make some types of attacks more difficult. I mean, in this case, it doesn't really matter because it's such a simple target. But as you mentioned for my previous talk, I wanted to actually put a code payload in and have that executed. So if that chip had been a Harvard architecture, that would have been a lot more difficult to actually get that into an executable area. You'd see different effects depending on the type of the chip. So on a RISC chip, your instructions are going to generally be all the same length. So you're going to have most likely some effect on this instruction, and then the rest of the code is going to execute normally. If you're on a CISC chip where the opcodes are different lengths, then you can have an effect where you might cause your opcode to be read as an incorrect opcode. in which case it's going to end up executing from the middle of the next instruction. And so in this case, you can have a more wildly different code flow.
Thank you.
Great. Thank you.